If you've ever looked at a fast-moving river or the smoke rising from a cigarette, you've seen turbulence. It looks like total chaos. To most, it seems impossible to calculate. But in 1941, Andrey Kolmogorov looked at this chaos and saw a hidden, universal order. The theory is titled, "The Local Structure of Turbulence in Incompressible Viscous Fluid." Let's break down these three key terms. Incompressible means the fluid doesn't squish, like water. Viscous means it has internal friction, like honey, and a high Reynolds number. That's where the real chaos begins. Think of the Reynolds number as a tug of war. On one side, we have inertia, the fluid's desire to keep moving. On the other, viscosity, the fluid's desire to stick together. When the Reynolds number is high, inertia wins by a landslide. The flow breaks apart into a chaotic mess of swirls. Kolmogorov realized we can't predict the exact velocity of a single drop of water. It is a random variable. So, he introduced a clever trick. Don't look at the point, look at the difference. He defined the velocity difference W between 2 points close to each other. This is the core of the coordinate shift in equation 2. Why the difference? Because the big movement of the river, the mean flow, doesn't tell us about the nature of the turbulence. The turbulence is in the shaking, the relative motion. Definition 1, local homogeneity. Inside a small enough domain, the statistics of these velocity differences don't change based on where you are. Think of a storm. The wind might be 100 miles per hour here and 80 over there. But the tiny swirls of dust behave the same way in both spots. Now for the secret sauce, the energy cascade. Definition 2 states that turbulence is also isotropic. It looks the same in every direction. Kolmogorov described a bucket brigade of energy. It starts at the large scales L. Imagine a giant paddle stirring a pool. This creates massive pulsations. These big swirls are unstable. They break apart into medium swirls, and those medium swirls break into even smaller ones. Finally, the swirls get so small that viscosity takes over. The internal friction turns that kinetic energy into heat. This is dissipation, epsilon. To quantify this, we look at structure functions. BDD measures velocity change along the line connecting 2 points. We call this longitudinal correlation. BNN is the transverse correlation. It measures how the fluid shakes perpendicular to that line. Because the fluid is incompressible, these two aren't independent. Kolmogorov derived equation 12, showing that BDD and BNN are geometrically locked together. Now we enter the inertial subrange, the middle ground. Here, the swirls are too small to be affected by the giant paddle, but too large to be affected by viscosity. In this zone, Kolmogorov's second hypothesis states that the velocity depends only on two things: the energy dissipation rate epsilon and the distance r. Using dimensional analysis, there is only one way to combine epsilon and r to get a unit of velocity squared. This leads us to the most famous law in turbulence. Equation 23, the 2-3 law. The correlation BDD is proportional to epsilon to the 2/3 times r to the 2/3. What does this actually mean? If you double the distance r between 2 points, the shaking doesn't double. It increases by the cube root of the square. This law is universal. It works in a cup of coffee, in the atmosphere of Jupiter, and even in the blood pumping through your heart. Finally, Kolmogorov showed that in this range, the transverse shaking is exactly 4/3 times the longitudinal shaking. Chaos is actually restricted by geometry. Kolmogorov's 1941 paper taught us that chaos isn't just a mess, it's a cascade, a rhythm of energy falling from the sky down to the smallest molecule. Order from chaos.